Hey, so in this video, day 36, we're going to be talking about how, a little bit more about ratios and how scale factor and ratio affects perimeter and how it affects area. Oh my. So pause the video, try the launch, which is just question 1, 3 minutes. If you need a little hint for area and perimeter, it's included. All right. So in this figure, we have a height of 3 and a width or a base of 1, 2, 3, 4, 5, 6, 7, 8. 8, right? 2, 4, 6, 8. 8 indeed. So the perimeter will be all the sides added together. And in a rectangle, opposite sides are congruent. So if the base is 8, then the top of the base is 8. If one height is 3, then the other height is 3. So perimeter is going to be 3 plus 3 plus 8 plus 8. So 16 plus 9. What's that? 25? Yep. So P is 25. Now area is just the base times the height. It's just 3 times 8, which is 24. So this is a nice little intro. Area is not always bigger than perimeter. Typically is. As shapes become larger, the area will always be bigger. But for relatively small shapes, perimeter will be bigger. Okay. So, alenchos. This is like a... You won't really hear this vocab word. This is a Greek word. It's kind of connected with this philosopher named Socrates. And it was something that he did. It was like this questioning to get at truth. It was like a cross-examination and interrogation. It was his method of analyzing and critiquing people's reasoning. So this is my alenchos to you. How do you know if two polygons are similar? What must they have in common to be considered similar? And then what kind of transformation creates similar figures? So pause that, reflect on it, and answer those questions. So shapes are similar if they are the same shape and size. Okay. What must they have in common to be considered similar? Same ratio / scale factor. Right? The sides have to grow at the same scale factor. And then what kind of transformation creates similar figures? Dilation, as we learned in the previous lesson. Alright, so that's like just a warm-up, kind of to get you prepared for today's lesson. And we're going to be accessing it through using ratios, through using that scale factor. So read the investigation, try it out. And then unpause it and come back whenever you need. Alright, so using equal ratios show that these rectangles are similar, meaning same shape but not necessarily the same size, meaning they have the same scale factor, the same ratio of sides. Okay, so if I take my heights, which I'm going to color code as blue, so this height is 2, and the corresponding height is 7. That has a value, okay? Actually, I'm going to do it the other way. Oops. Yeah, I'm going to do the image. I'll call this the image and this the original. I'm going to do 7 over 2. And I'm going to see that has a value. So I turn on my handy-dandy graphing calculator. 7 divided by 2 is 3.5. So if these shapes are similar, then the bases needs to have the same ratio. So now I look at my base. It is 21 over 6. Use my calculator again. 21 compared to 6 with division is also 3.5. So, yes, they are similar. That is how I know. What is the scale factor for this dilation? Well, it is simply 7 over 2, which is 3.5. Okay, that is how I'm going for my original, right? 3.5 times 6 will give me 21, and I'll show you that. 6 times 3.5 is that corresponding 21, and 2 times 3.5 is that corresponding 7. Now here is a tricky one. We kind of talked about this the other day. Could you use a different ratio to demonstrate that these rectangles are similar? In other words, is there another scale factor? Or is 3.5 the only one that works? Pause the video, write what you think, and then come back. If you thought yes, then what was that ratio? If you said no, what was your reasoning? Now, I kind of gave it away at the beginning. I think yes, because nowhere in here did they say that the small one had to be the original. Maybe the small one is the image, and maybe the original is the big one. And the only way that can happen is if you have a scale factor that's less than 1, but greater than 0. And 3.5 is clearly bigger than 1. So I'm going to assume the opposite. I'm still going to use this concept of original over image, but now I'm going to say my image is that height of 2 right here, and I'm going to divide that by the corresponding original, 7. And now I can see my scale factor is going to be this funky decimal. It's going to be woof, whatever that is. Okay, that's my other scale factor, and I'm going to change this to approximately 0.286. 3 decimal places is always good, and I'm writing 6 because 7 is greater than 5, so that 5 turns into a 6. And I'll show you that this works. If I take that scale factor, that decimal, and I multiply it by my original base, I expect to get my image of 6 times 21. And that works. And the same thing will work with 7, giving me 2. All right. Now, Plato, the student of Socrates, claims that these figures are not similar. This guy, I don't know, man. He says they're not similar. Maybe he knows something we don't. When he compared the heights, what he wrote was 2 over 7. And if we look, yeah, 2 and 7 are the heights. All right, that's good. Then he compared the bases and got 21 over 6. And if we look, yeah, 21 and 6, they are the bases. Okay. Why is Plato having trouble? Explain what he's doing wrong completely. Well, if we type this in, 2 divide 7, right? That's that weird scale factor, right? And then 21 divide 6 is that friendly scale factor. So he's kind of discovered both scale factors. It's just that he's comparing apples to oranges. He's mixing up his original and his image. In one case, he's using the small one as the image, right? He has that on top. In the other case, he's using the big one as the image. He's swapped these ratios. So if we just fix it as 1, if we go back to our, the big one's going to be the image and the little one's going to be the original. What he's done is that ratio right here, the 2 over 7, that 7 belongs to the image. So the ratio is where the original is divided by the image. And then in the other one, he has the image divided by the original. So what has he done wrong? Plato has mixed up his original and image in his ratios. In other words, he set up, I swear I can spell, he set up his ratios poorly, incorrectly. Man, Plato, what are you doing? You should go back and talk to Thales and, Euclid, that's the one. Study some more geometry. Get your head out of the clouds, like Euripides said. Oof. Investigation 2. All right, this is kind of like an application. So you got 3 cases here. They are similar. We are promising you there exists some scale factor that creates proportionality, that creates all of these corresponding sides. So take what you know and apply it, and just be careful that you're comparing, corresponding sides to corresponding sides. All right, so if you came back, the first one I'm going to do with, I'll do it both ways. I'll do the scale factor. I'll pretend this is the image. This is the original. I can see my image is 4, my original is 2. 4 over 2 is a scale factor of 2. So if I apply that logic, dilation of 2, pass 6 through it, x certainly needs to be 12. The other way I could do it is I can make a proportion. I could say, yo, you know that fraction right there that I have? I'm just going to use that. That's one of my ratios. I'm comparing my heights. And then I'm going to compare my bases. So if I start with the image here, if I start with the big one, then in my other ratio, I need to start with the image. I need to start with the big shape. So that x, even though I don't know what it is, I know it belongs to the big shape. And that's going to correspond to the small base in my original. So now I've got a proportion, because we don't want to make that mistake that Plato did. We don't want to swap these around. That's incorrect. That's mixing it up. So we want to be consistent in how we label this. I've got something from my image on top, something from my image on top, something from the original on the bottom, something from the original on the bottom. And now I'm going to use cross multiplication. 4 times 6 is 12, 24. And that times x is 2x, divided by 2, divided by 2. X clearly equals 12. Same answer, multiple methods. And this proportion, I think, is a little bit easier, and it's certainly going to help you out in this last one. So if I apply my proportion method, I've got this height of x, and then that's going to compare over here, that height of x. And I can see, like, this angle points to that right angle that belongs to that side. And that's kind of the same setup here. It's just been, like, rotated around. So x over 6. And then if I start with the big shape, right, the big, then for my other ratio, I need 4 on top and that corresponding 3 on the bottom. And notice how the red points to the blue, the red points to the blue. Anytime I have a proportion, I can cross multiply. I get 3x. I bring down my equals. I get that 24 again. 3 divided by 24. Man, I was never ever good at division. Is that 8? I just don't know. Sure, my number sense is fine. It's 8. Okay, x is 8. I challenge you to figure out what the scale factor was. Okay, now in here, I do not deny that there is a way that you could solve this using scale factor. I know it. There is. But it's not easy, because you want to take your image and divide it by the original to find scale factor. The issue is you have no idea what that is. You need to know the scale factor. And you can't use this side because that's also a big question mark. You have question mark over 3, and that's just, more nonsense. What you could try, how would I do this? Oh, yeah, now I remember. You are going to solve this way different, but this is how my mind solves this. I see this perimeter thing, right? And I go, okay, well, I could calculate the perimeter of my original. It's very simple. This side is 3, and this side is x. The perimeter is 3 plus 3 plus x plus x. The perimeter is 6 plus 2x. And what I'm going to do is this trick. I'm going to take that top part, x, which compares to that 21, and I'm going to set it equal to my perimeter. I'm going to compare perimeter of, you know, the little to the perimeter of the big. And that will work. That will work for this problem. 6 plus 2x. And if I do my cross multiplication, right, that's 60x. And then I just got to be careful with this. This is 21 times the quantity, 6 plus 2x. I distribute. I have more important things to do than 21 times 6 in my head. It's 126, so I'm going to have 60x equals 126 plus 42x. Subtract 42x. 42, so what's that? 18x. So I'm going to get 18x equals 126. Divide by 18, divide by 18. X is going to equal, divide 18, 7. I can tell you that this side was 7. That, in fact, the dilation that took place was 21 over 7, was 3. This was a scale factor of 3. And there's another way you could do that. Like, this method is where we're ending with the lesson. It's this idea that you can use perimeter in your comparisons. You won't be able to use area in your comparisons. This problem is kind of meant to prompt you that there's something going on, that there's something extra you need. But honestly, if you solve this, bravo, because chances are you approached it this way. You worked backwards. You were like, well, if perimeter is 60, well, I know that came from adding up all the sides. So I'm going to call this needs to be 21 because that was 21. And I'm going to call this y and y. And you are probably doing this in your head, but you can make an equation. You say, well, 2y and 2 21s, meaning 42. I subtract 42, subtract 42, that's that 18 equals 2y, divide by 2, divide by 2. Y is going to equal 9. And now you can say, aha. So I've used, I swear this will erase, I have used their perimeter and that 21 and this 21 to work out that there's really 18 left for both sides, and since both sides are equal, I could split that equally amongst them. And now I can compare that 9 to that 3, right? That 9 over that 3 is that scale factor of 3. And that's where you could go backwards. You could be like, okay, well, 21 divided by 3 is that 7. And that's probably how you solve that problem, okay? All right, so now we're coming to the end of the lesson. Let's see where we are. 18 minutes in, probably? Yeah, hey, I have good number sense. Good time. Okay, let me minimize this. So, now we're getting to the teacher. Socrates noticed that the ratio of the perimeters of the two figures is equal to the ratio of the side lengths. That's what I did originally. I did what Socrates observed. He's asking about the area. He's saying, does the area grow the same way? And what we're asking you to do is just manually calculate area and perimeter. So area is the easy one. It's the base of 7 times the height of 3. So that's 7 times 3, which is 21. Now, perimeter, right? Opposite side's 3, opposite side's 7. Right? That's what I'm fishing for here. Perimeter is going to be 7 plus 7 plus 3 plus 3. Well, that's 10. And this is 10. So perimeter is 20. Okay? So I'm going to clean this up. I'm going to say... actually, I'm going to leave it as is. And what I'm going to do is highlight my perimeter, highlight my area. We're going to test this theorem. Test Socrates' question by sketching the enlarged rectangle by a scale factor of 3. So if we take this original height and we pass it through a dilation of 3, Well, that 3 is going to get multiplied by that 3 and become 9. This base of 7 is going to pass through that dilation of 3, and it's going to become 21. So now, if we calculate area, well, that's 9 times 21. I have no idea what that is. 9 times 21. It's apparently 189. 189. So this, and I'll circle this in purple. I'm going to do the same thing here. I'm going to put my areas in purple. I'm going to highlight the perimeters. Now I'm going to calculate perimeter, 9, and then 21. Well, that perimeter is 42, because 21 and 21, and 18, and 18, because 9 and 9. And that becomes 60. Okay? So now I can see that, well, my perimeters are 60 and 20. And remember, my scale factor was 3. So if I compare my perimeters with a ratio, if I do 60 over my original 20, I can see that spits out my scale factor of 3. But now, when I compare my areas, when I do the image 189 over the original 21, I am not going to get 3. I know I'm going to get 9. You might be asking yourself, how do you know you're going to get 9, Mr. Elias? Are you doing mental math in your head? No. I know how area grows. I know it has to be 9. You might be saying, well, why did the area not get multiplied by the scale factor of 3? Why is it that, right? Because what you expect to happen is that 3 times 21, you expect this this area to be 63, because 21 times 3, your scale factor is 63. But that's not how it grew. It didn't do that. The way we use 21 to get 189 is 21 times 9. That's the 189. So the real question here is, why was it 9? Where did the 9 come from? Okay. Does the perimeter triple? Yes. Does the area triple? No. What happens to the area is it grows by 9. And that's kind of where you're going to apply this. Let's see what I'm doing for time. I can do this. And I'll show you what's going on here. So I got my sketch pad. I'm going to make a rectangle with a height of 2 and a base of 5. Okay? I'm going to hide these. And I'm going to dilate this rectangle about point A with a scale factor of 3. And when I do that, I get this. And what's really neat about this is what these numbers represent is the area. All right, if you look at this shape, and I'll color it blue, my original has an area of 10. Because look at the square units. It's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It is 2, right, my height, sets of 5, my width. It is 2 times 5, 10. Now, the area here, it's not just tripled. It's not 3 of these rectangles. Because if it was 3 rectangles, that would be the 30. That would be like my original area of 10 times the scale factor of 3, 30. And you can see that 3 rectangles do not fit in here. And here's why. Because when you do a dilation, all the sides get multiplied by 3. So your base gets tripled. That's why there's 1, 2, 3 rectangles there. But so does your height. Your height of 2 gets tripled. So you're going to get 3 more rectangles here. But then, because you have 3 heights now, 3 heights of 2, you need to have, right? You have 1, 2, 3 heights of 2. You need to have 3 rows of 5. And that's kind of what's going on here. That's kind of what's going on here, okay? That height of 2 gets times 3. It becomes 6, right? 2 times 3 equals this 6. And, 3 times my original 5 gives me that 15. And 6 times 15, I believe, is going to give me 90. 6 times 15, is 90. And here's what's really going on. If we look at the area formula is base times height. Okay? And when you dilate area, what's happening is your base, right? Your base is getting multiplied by the scale factor. Your height is also getting multiplied by the scale factor. So your scale factor doesn't show up just once, it shows up twice. And anything times itself is that thing squared. And that's where we're getting the 9 from. Because our scale factor is getting multiplied by our base and our height. It's happening twice. It's happening squared. So if we just take our original area, and instead of multiplying it by the scale factor, we know we take our original area and just multiply it by the scale factor squared. And I'll show you that this works, all right? I will go back into GeoGebra. I will try and select everything, which won't work. I'll delete, and I'm going to make a new polygon. We'll make it somewhat small so it's manageable. And I can see that the area is 12. And I'll tell you what. I'm going to pick a scale factor of 7 because that's how could I possibly know what the area is going to be. All right. But what I'm saying is if you take your original area of 12 and then instead of multiplying it by your scale factor of 7, because the base is going to get times 7 and the height is going to get times 7, I need to take that scale factor of 7 and I need to square it because that 7's getting multiplied 7 in the base and 7 in the height. So I know if I take my original area of 12 and I multiply it by my scale factor squared, that's going to give me the dilated area. 588 is the dilated area. And I'll show you that's the case. I'll take this figure, I'll dilate it about a point, and then I'll make my scale factor, that's 7. And you will see we have equivalent areas. I've got my original 12, and I've got my new 588. And that is what's going on. I hope I explained it properly. I hope I explained it well. This is a tough thing to see. So now we want you to apply that to these. We want you to figure out what the image is, what the original, and then use that to determine scale factor. So here it's 8 over 2. So my scale factor is 4. I am telling you the perimeter. I am telling you the area. You're supposed to use your scale factor and these to calculate the image. So I'll model it in the summary, and you can try it on the last one. and then share it with me. So I know perimeter grows at the scale factor. If I take my original perimeter and I times it by the scale factor, that's going to be how it works. So my original perimeter was 14. My scale factor was 4. 14 times 4 is 56. That is my dilated perimeter. Now, area, on the other hand, is the original area. And it's not times the scale factor. It is times the scale factor squared. So if I take my original area of 10 and I times it by my scale factor squared, if I do not 10 times 4, if I square 4, not 4 times 2 either, right? It's 4 squared. It is 4 times itself. It is 16. If I do 10 times 16, my 4 squared, my scale factor squared, that's 160. And that's what that area should be. Okay? Yeah, I'm not going to show it in here. This video is already going too long. You do the exit ticket and show it to me. I hope this lesson went well. And so long as it keeps on going, I'll keep on making the videos. Thank you so much, and I'll see you next time.